Let me start. This is the sixth edition of the lecture of the name of Professor Stanisława Łojasiewicza, our greatest professor. This lecture is going to be the greatest mathematical event in Krakow. This is the sixth edition. Before this, our previous speakers were Wow, Richard Hamilton, Bernard Malgrange, Neil Trodinger, and Fernando Coda Marquez, mathematicians of the world knowledge. And now our speaker today is Professor Noga Alon from Tel Aviv. First of all, I would like to welcome Rector Professor Prof. Leidger, who represents the University Authority, and welcome everybody. Let me ask Rector to say a few words.
I think that this is it's so big audience. Yes, it should work. Yes. Thank you very much for inviting us to such important events, because this is the real life of the university. And we are right now in a period when we look for application. But I'm also representing the basic sciences. I'm a biochemist. Maybe for me it's the most difficult time, because from medicines we expect quick application. I know that it's not always possible, and you represent the knowledge that for years and years create a certain solutions that may or may not be used very quickly. And I really appreciate that, really, privately. But right now let me welcome our excellent guest from Tel Aviv University. I know that there is some kind of collaboration between the Tel Aviv University and the Jagiellonian University Department of Mathematics and Informatics. And on behalf of the authorities of the Jagiellonian University, Rector, Professor Wojciech Nowak, and of course myself, it's a great honor to be here. And I am also very happy to see such big audience. It's not always that in every seminar we have so many people so quickly, so I believe that this kind of the tradition that is now emerging, the tradition of Łojasiewicz lectures, it's a great idea. So I wish you, I won't understand anything, therefore I will soon leave. But I believe that you will have a great afternoon. So I wish you all, and thank you very much, Professor Alon, that you came to Krakow and decided to give that lecture. Thank you very much.
I ask Professor Jarosław Grytczuk to say a few words about today's speaker.
I know that you are waiting for the lecture, but let me say a few words to give you a silhouette of our speaker. So it is a great pleasure and a great honor to present Noga Alon. He is now a Baumritter Professor of Mathematics and Computer Science in Tel Aviv University in Israel. He received his PhD in mathematics at the Hebrew University of Jerusalem in 1983. But he is a frequent visitor in many famous institutions. For instance, he visited MIT and the Institute for Advanced Study in Princeton, the IBM Almaden Research Center, Bell Laboratories, Bellcore, and Microsoft Research. He joined Tel Aviv University in 1985, served there as a head of the School of Mathematical Sciences, since 1999 and 2000 and supervised more than 20 PhD students. Since 2009, he is also a member of Microsoft Research in Israel. He serves on the editorial boards of more than a dozen international journals and has given invited lectures in plenty of conferences, including plenary addresses in the 1996 at the European Congress of Mathematics and in 2002 at the International Congress of Mathematicians. He published more than 500 research papers, and he is also a great collaborator. The number of his co-authors exceeds 400, as I learned today. And among these co-authors, there are some people from Poland and even one person from Krakow. Okay, so prizes. He received lots of prizes, just to mention a few. The Erdős Prize in 1989, the Feyer Prize in 1991, the Polya Prize in 2000, the Landau Prize in 2005, the Gödel Prize in 2005, the Israel Prize in 2008, the Emmet Prize in 2011, and an honorary doctorate from ETH Zurich in 2013. And today we have him here, and he will speak about sign rank and its applications, oh my God, in in combinatorics and complexity. So, please.
Thanks. Thank you for this very nice introduction, and thanks for the organizers for the invitation, and I want to thank you all for coming. I should apologize that I have a new laptop, and apparently the new version of PowerPoint is not exactly compatible with what we have here, so I'll use a PDF, which means that the animation is not here, but you can try to pretend how things would look if they would be moving. So this would, so it's a great pleasure and honor to give this Łojasiewicz lecture. And the title is Sign Rank and its applications in combinatorics and complexity. And this will combine combinatorics and geometry and probability with some tools from real algebraic geometry. Now, as you probably, or many of you probably know, Łojasiewicz was working mostly in analysis, in the study of ordinary and partial differential equations. But one well-known result of him is Łojasiewicz inequality. So that's a result in real algebraic geometry. And one of the things we will use in the lecture today will be some other inequalities in real algebraic geometry. There aren't so many results in general in real algebraic geometry, so people prefer complex because it's a closed field, and it's but the ones that exist are nice and interesting, and I'll try to convince you that that it's worthwhile knowing them. So many of the problems here are motivated by questions in theoretical computer science and in combinatorics. And most of the new results I'll mention are from a recent joint paper with Shai Moran and Amir Yehudayov from the Technion. So let me start by telling you what is a sign rank of a matrix. We have a real matrix, and let's assume that the matrix does not have any zeros, so it has non-zero elements. That's a matrix A, and the sign rank of it is a minimum possible rank of a matrix B, so that every entry of B has the same sign as the corresponding entry of A. Let me check, incidentally, that you can hear me in the back also, so it's okay. Yeah. So it's. I think it works. I can hold it closer to it, but okay. Okay, but if you stop hearing me, then make some signs and do it. Okay, okay. Thanks. So, so again, the sign rank of a matrix A, as I said, is the minimum possible rank of a matrix B, so that every element of B has the same sign as the corresponding element of A. So what I wrote here is that for every I and j, Aij times Bij is positive. This means that when Aij is positive, Bij also has to be positive, and when Aij is negative, Bij also has to be negative, and we try to minimize the rank. So that's a simple to define, but it's quite complicated to understand how it behaves. Here I show you one example. So this is this matrix that sort of looks like a signed version of the identity matrix. It is negative on the diagonal and is positive everywhere else. And the claim is that the sign rank of this matrix is 3. Okay, it's a 4 by 4 matrix. And let's see at least one direction of it, the upper bound. So we can replace all the negative elements on the diagonal by -3, and all the positive elements, let's keep them as +1. And you see that now just the sum of elements in every row is 0, and because of this, the codimension is 1. So this matrix has rank 3, and it has the same sign pattern as the matrix A. So it means that the sign rank of this matrix is at most 3. And it can be shown, I'll not show it here, you have to think about it a little bit. It can be shown that it's exactly 3. It is not less than 3. And in fact, it will follow from some of the things I'll say later, although maybe I'll not mention it again, that for every identity-looking matrix, a matrix which is negative in the diagonal and positive everywhere else, if it's at least 4 by 4, so maybe it's n by n, then the sign rank is always exactly 3. Those of you that have been in the preparatory workshop yesterday have seen a proof of this, but let's just focus on this example. So this explains us what the sign rank is. And this sign rank has an interesting and simple geometric interpretation. So the claim is that the sign rank of any matrix A is a minimum dimension D, so that we can assign to each row I a hyperplane through the origin in dimension D. And for each column J, we assign a point, P sub J, in dimension D. And what we want is that the jth point, Pj, lies in the positive side of the hyperplane Hi, even only if Aij is positive. And if it is negative, then the point Pj lies in the negative side of the hyperplane. And it's not difficult to show that this is equivalent to the definition of a sign rank, just because the rank of a matrix is D, even only if you can write it as a product of an n by D matrix by a D by n matrix, and then the rows of the first matrix represent the hyperplanes, and the columns of the second matrix represent the points. So, yeah. So I have here an example. Here it is. So this shows that a sign rank of the matrix that you see here, -1, -1, -1, -1, and so on. So the sign rank of this matrix is 2. So this means that I should assign every row a hyperplane, which means a line, because we are in dimension 2, so just a line. And then for every column, we would have a point. And we want the points to lie in the positive or negative sides of the line, depending on the sign of the actual matrix. So let's assume that when we look, we stand on a line, and we look at the direction of the arrow, then on our right side, this is the positive side of the line. So you see that the positive side of the first line, H1, is what's below it, right? Because, and indeed, if we look at this example, so all the points are in the negative side of this H1, and because of this, in the first row, what we have is -1, -1, -1, -1. And in the second row corresponds to the line H2. So if I'm standing on H2 and I'm looking at the direction of the arrow, then in my right side, I see P1. So that means that in the first entry of the second row, we should have +1. And in all the other places in this row, we have -1, right? And so on. So the sign rank of this matrix is at most 2, because we can represent it in such a way. And it's easy to see that it is not 1. You see the sign rank is 1, then every row is a product, a scalar product of the first row. So it means that if the sign rank is 1, then all the rows should have either the same sign pattern as the first row or the negative of it, the inverse of it. But this is not the case here, right? The second row is not equal in the signs to the first row and not to its inverse. So the sign rank is at least 2, and because of what we said, it's exactly 2. Okay, so that's an example of a sign rank. And there are several reasons to look at the sign rank of a matrix, and I'll tell you very briefly about this, just because so it will be more or less the buzzwords, but I'll try to explain something about each of them. So the first one is a result of Paturi and Simon from 85, and this says that the sign rank of a ±1 matrix determines the so-called, and I'll say something about it, unbounded error communication complexity of the function described by the matrix A. Again, for those that heard the lectures yesterday, we heard something about it, but I'm not going to assume anything. So what is this unbounded error communication complexity? This is the minimum number of bits that have to be exchanged between two players, Alice and Bob and Alice. They know the sign matrix A, and they can agree on a protocol. And now Alice gets a row I, so she knows a row, and Bob gets a column J, and then they have to exchange messages. So maybe Alice sends a bit to Bob, and Bob sends a bit back, and so on. And after such an exchange, at the end, they have to know that they have to guess that the value of A in place Aij is plus, and their guess has to be right just with probability that is bigger than 1/2. So that's why it is called unbounded error communication complexity. So to be right with probability 1/2, this is trivial. They don't have to look at the matrix at all. They can just guess randomly, and it will be right with probability 1/2. But to be slightly better than 1/2, they have to do something. And the minimum number of bits that they have to exchange for the worst possible row and column in the best protocol is called the unbounded error communication complexity of this matrix. And it can be shown that this is essentially the log base 2 of the sign rank of the matrix. So that's one reason to look at the sign rank of a matrix. Let me show you the compulsory picture when you look, when you talk about communication complexity. Usually show Bob and Alice. So here they are. they are, so the choice of the names Bob and Alice is because the initials are A and B. So it's convenient to denote them by A and B. I once saw a lecture given by Ron Rivest, so he's the R from the RSA crypto system. And when they presented him, the host presented him at the beginning, he said that we are happy to have Ron Rivest. He is famous for the invention of the RSA crypto system and also for his book with Corman and Liserson, and also a few other things. And somehow you could see that Rivest was not completely satisfied with the presentation. Unlike me, I was very happy with Yarek's presentation. And he came and he started his talk by saying that the host forgot to mention his most important contribution, and this is the invention of Bob and Alice. So apparently he's the first one who started to use these names, and from then on they are used in communication complexity. So you see here Alice and Bob. There is this matrix. Alice has a row I and Bob has a column J, and then they exchange bits. So Alice sends maybe 0 here, and Bob sends back 1, and then she's sending 1, and so on. And after a while, then they know that, or they guess that the value of the matrix in place ij is positive. And they have to be right with probabilities that just exceeds half by a little bit. And as I said, it can be shown, and it's not very difficult, that the minimum number of bits that they have to send for the worst I and j at the best protocol is essentially the log of the sign rank of the matrix. So this is one reason where sign rank appears. Here is another thing, and again, I'll not say much about this. So it's related to what is called the large margin classifiers in computational learning. And this is when we try to learn concepts by embedding them in an Euclidean space. So that goes back to something called the Perceptron algorithm, on which Rosenblatt wrote in the 50s. So here we think that, again, we have a matrix of pluses and minuses, and the rows represent the concepts. The columns represent the examples. So we have some row, some unknown row, and we have to learn it by getting, maybe randomly, some samples of columns. And for each such column, we get the value of the sign of the matrix in this place of this column. And we want that after we get some random examples, we will be able to predict with good probability the sign of the next given column or sample like this. Now I know, so this is not supposed to make too much sense for those who didn't hear about learning before. Again, people who came yesterday heard about it before, but at least it gives you the flavor of things. So for example, if the concepts and the matrix corresponds to hyperplanes and points in dimension d, this is when the concept is really a hyperplane and we try to learn it. So for each point, the value of the point on this concept will tell us if it lies in the positive side of the hyperplane or the negative side. So someone gives me points one by one and tells me if they are on the positive side or the negative side. And after a while, I know quite a lot about this hyperplane. And you see here some picture, which is, again, in dimension 2. And we have this hyperplane, and we have these red points that are on one side of it and blue points that are on the other side. Now, there are somehow good algorithms. So this is this perceptron algorithms that learn hyperplanes. If I have an unknown hyperplane, then I know well how to learn it when someone gives me points and tells me for each point if it's on this side or on the other side. And one possibility is to try to learn general matrices or rows of general matrices by embedding them in some low dimensional Euclidean space, and preferably we want to have what is called high margin, namely that for each hyperplane, the points that are on the positive side will not be too close to the hyperplane. They will really be on the positive side, and the same for the points on the negative side. And somehow the signed rank tells us how well we can do it. Can we do it in low dimension, and can we do it with high margin? Again, as I said, I only expect this to give you something about the flavor of things. So this was about sign rank. And another notion that, that I want to talk about is the so-called Vapnik-Chervonenkis, or VC dimension of a matrix. Okay? So that will be another definition that has to do with a sign matrix. Let us have an n by n matrix A. So all my matrices today will be square, but everything works equally well for rectangular matrices, but just simpler to focus on square matrices. So if we have a matrix of plus and minus ones, we say that a set I of columns of this matrix is shattered by the matrix if for every subset of the set of columns, we'll soon have an example, for every subset, we have some row which is negative on these columns, in this of the subset J, and are positive on the other elements of I. Okay, so this means that the set of columns is shattered, and the VC dimension of A, which is denoted by a VC of A, will be the maximum cardinality of a shattered set of columns. So for example, you see this matrix here. This is a 5 by 5 matrix of pluses and minuses. And what I claim is that the set 2, 3, columns 2 and 3 are shattered, because you see here in red, you see that for each of the possible 4 configurations of pluses and minuses on these 2 columns, we have some row on which we see this configuration. And that exactly means that for every J, which is a subset of 2 and 3, you have some row which is negative on J and is positive on I minus J. So here we have in red these 4 rows that give us the 4 possibilities on these 2 columns. And of course, the VC dimension cannot be bigger than 2, because if we want it to be 3, then we need at least 8 different rows, because we have to have all the 2 to the 3, or the 8 possibilities as projections, but we have here only 5 rows. Right? So the VC dimension here is exactly 2. Now, VC dimension also appears quite a lot in applications, and naturally it was introduced by Vapnik-Chervonenkis. As I said, it is called after them, so after the initials, and it plays a central role in computational learning, specifically in this model introduced by Valiant, which is called the PAC learning model. PAC stands for probably approximately correct, let's say. And there is a theorem, so that's a very basic theorem in this theory, and this is by Blumer, Ehrenfurth, Hausler, and Wormuth. And it's again from the 80s. And it basically says that if we know the VC dimension of a matrix, we know quite well how many examples we need in order to learn a row of a matrix. And again, I'm not going to be more formal here, but let's just say that the VC dimension kind of captures the learnability of this matrix. The VC dimension is also related to communication complexity. So what is written here is that it basically determines the so-called one-round communication complexity of a function with respect to product distribution. That's from another paper by Kramer, Nissan, and Ron. And it basically says the following. So again, we have this matrix of pluses and minuses that represents some function. Now, so far, I only mention unbounded error probabilistic communication complexity, which means that we have this random protocol of Bob and Ellis to exchange messages, and they have to guess the right value of Aij, if it's positive or negative, with probability that is bigger than 1/2. Now you could ask about a different notion of random algorithm, and this is when actually we have a distribution on the possible entries, Ij. So suppose we have this matrix, and we have some distribution on the possible pairs Ij, and what we want now is a deterministic algorithm that on the average, with respect to this distribution we have on the entries Ij, it will be correct with probability bigger than 1/2. So it can be shown that this notion is exactly equal to the unbounded error probabilistic communication complexity, and this is because of something that is called Yau's lemma, but it's basically just the min-max theorem of game theory. And because of this, it makes sense to ask also what is the communication complexity we need if we assume that we have some distribution on the possible entries, and we assume something about this distribution. So if the distribution is a product distribution, it is determined by a product of distribution on the rows and distribution on the columns, then if the VC dimension is small, then we can really do it, do the whole protocol with, and succeed with probability, say 2/3 or something that is bounded away from 1/2 in one round with a small number of bits. Okay? Again, I'm not saying too much about it. And I also wrote here that the VC dimension appears in computational geometry, in combinatorics, in probability, in the study of approximation algorithms. So it's really a basic concept. And we want to understand something about the relation between signed rank and VC dimension. And understanding it will tell us, will give us some applications about separation results with respect to communication complexity and to learning, and maybe in some other areas as well. So, so in general, it's fair to say that the sign rank of a matrix is small if the matrix is simple, right? So if, for example, all the rows look the same, they all have the same sign pattern, then the sign rank is 1. If all the rows, so somehow if it's simple, then it has small sign rank. Also, if it's simple, it has small VC dimension. And we want to understand the relation between the two. And specifically, I want to denote by f of n and d. So this will be the maximum possible sign rank of a matrix A, where the maximum ranges over all n by n sign matrices A, so matrices with ±1 entries, whose VC dimension is at most d. Okay, how big can the sign rank be? And if we don't specify the VC dimension, so this f of n will be the maximum of f and d, where the maximum is taken over all d. So this just means how big can the sign rank be of any n by n matrix, sign matrix. Okay. So here are some old results. There's something in an old paper with Peter Frankel and Wojta Redel. And this, it begins to be quite frightening when you start mentioning results in papers of yours and you realize that this was written 30 years ago, but somehow in recent years it happens more and more often. I'm sure some of you know it already, and the others will find it out sometime later. But so here is something we could show, that this f of n, so the maximum sign rank of an n by n matrix is never more than about n over 2. So if you have any n by n matrix of plus and minuses, you can always put their positive and negative numbers according to the signs and have the rank about n over 2. So some much smaller than n. And on the other hand, there are n by n sign matrices whose sign rank is at least linear in n. So maybe n over 20 is 1 over 20. It can be improved here, but it's some numbers that is still much lower than the upper bound, 1/2. And I'll tell you something about the proof of this, and something maybe more related or more interesting to the purpose of the talk now, using similar method. So this is a more recent result by David, Ron, and Simon, and it says that for every fixed d, which is at least 4, this f of n and d is pretty big. So there are n by n sign matrices with VC dimension at most d, and the sign rank is at least n to the 1 minus 2 over d minus 1 over 2 to the d over 2. So for example, if d is 4, then this gives you n to the 3 quarters, I think. Okay, so those are. Now we want to understand this somewhat better. So to understand f n d, the maximum possible sign rank of a matrix of signs, n by n matrix with a VC dimension d. And here is something recent in this paper with Moran and Yehudayov. And it says the following. So the first part is simple, and this actually appeared in a much earlier paper. So if the VC dimension is 1, then the maximum possible sign rank is exactly 3 for every n which is at least 4. In fact, this an example, one possible example is this identity-looking matrix. So if we are negative in the diagonal, positive everywhere else, then the sign, then the VC dimension is 1, because it's less than 2. We don't have any row with 2 minus 1s, so the sign rank is only 1, and for every n which is a VC dimension is only 1, and the sign rank is 3 for every n which is at least 4. Now for every d, for every fixed d, this maximum possible sign rank of an n by n matrix with VC dimension d is at most some constant n to the 1 minus 1 over d. So for d equals 2, it's at most square root n. For d equals 3, it's most n to the 2/3 up to some constant, and so on. This is an upper bound that holds for every n and d. And then there are some lower bounds. So somehow the conjecture, I'll mention it, it will be written soon, I'll mention it now. So a possible conjecture is that indeed f and d is constant n to the 1 minus 1 over d for every d. So this would be interesting to show. The lower bound we know is a little bit weaker. So for d equals 2, it's almost right. So it's at least square root n over log n, and at most square root n by what is written above. So up to the logarithmic term, it behaves right. And then for 3, 4, and more, then you have some bounds which are not quite n to the 1 minus 1 over d, but are not far. So you see that for f and d, it's n to the 1 minus 1 over d minus something, forget the logarithmic term, and this something behaves maybe like 3 over d squared. So something that is pretty small for large d. Still, there is some gap between the upper and lower bound. And as I said, the conjecture here would be that this f of n and d is a constant n to the 1 minus 1 over d. So, now, there is something, so I just mentioned briefly something about explicit examples. There is a very nice result by Forster, and it says that for every, so that's from some almost 15 years ago, and this is, yeah, that's another manifestation of the same principles, that these results that I remember when it was proved, and it was not so long ago, really, but it turns out that it's 14 years ago, and this is that for any n by n Hadamard matrix A, the sign rank of A is at least square root of n. And there is something more general, so so by Forster and several other collaborators, that if you take the n by n incidence matrix A of a d-dimensional finite projective space, doesn't really matter what exactly I mean here, but it's some explicit matrix, and we change it to be a sign matrix. So that's why I wrote here a j minus 2a instead of a, because I want to change 0 and 1 to 1 and minus 1. Then the sign rank of this is at least n to the 1/2 minus 1 over 2 to the d. So, and we have a little extension of this, is that if you have a, so it's some bound in terms of the singular values of a matrix. If you give me some deregular Boolean matrix, and by deregular I just mean a matrix of 1s and 0s that has exactly d1s in every row and exactly d1s in every column, and then we can look at the singular values, the square roots of the eigenvalues of AA transposed. So these are all non-negative because AA transpose is a positive semi-definite matrix. The biggest one is D for any such matrix, and then you can look at the other ones. And it turns out that, again, if you take the sign version of this matrix, you change it to J minus 2A, which just corresponds to changing a 1 to minus 1 and a 0 to 1, then the sign rank of this is at least D over sigma 2. So this enables you to give many other explicit examples of matrices with VC dimension 2, for example, in sign rank at least n to the 1/4. I should say that using these eigenvalues or singular values bound, then this will never give us a bound that is bigger than square root n. It can be shown. So, so it will be interesting. As I said, we know that there are some matrices whose sign rank is linear in n, and it will be interesting to find an explicit example of some specific matrix that we can show that the sign rank is significantly bigger than square root n. Now let me mention quickly something about applications, and then I'll tell you something about some proofs. So here are applications because of the connection between sign rank and VC dimension to learning and to communication complexity. So the first one is that there are explicit n by n matrices A, so that the communication complexity with respect to product distribution will be a constant, whereas the communication, the unbounded error, even communication complexity, but with respect to general distribution, will be essentially constant log n, which is essentially the biggest that could be. Because one possible communication between Alice and Bob is that Alice just sends the name of her row, the name I, so this is log n bits, and then Bob knows everything because he knows the column and he can compute the thing. So in particular, for example, if they play on a projective plane, Alice has a line and Bob has a point, and they have to decide if the point of Bob lies on the line of Alice or not, then this is something that with respect to product distribution is very, very easy to solve. We just need constantly many bits because the VC dimension is very small. But on the other hand, with unbounded error, communication complexity, and general distribution, we basically have no non-trivial algorithms. The best that Bob and Alice could do is that Alice will tell which line she has, right? And then Bob will check. Okay? And this is even if they just want to get a slight advantage on the probability that they have the right answer. So there was some earlier examples that gave a square root log n, and this gives log n. Another thing is, so an application to learning, is that there are explicit n by n sign matrices whose rows can be learned by constantly many examples, again, because the VC dimension is very small in this PAC model of Valiant. But on the other hand, if we insist on learning them by embedding in Euclidean space, which people in computational learning do often, then there will not be any efficient thing. We will need high dimension, and we will need low margin, so somehow it will not work well. So there are these explicit examples. Here is something that is very different. That's a result in combinatorics or in asymptotic enumeration, if you want. And this is if we want to estimate the number of n by n matrices of plus minus ones in which the VC dimension is D. So the claim is that this number is at most 2 to the n to the raised to the power 2 minus 1 over D log n, which is probably tight up to the log n. And this improves some earlier estimate we had with Balog, Bolobash, and Morris, which had the higher power of log n, but also was much more complicated. So somehow this follows from these new things very easily. And finally, I'll mention that these things give us, or the proofs give us, an efficient deterministic algorithm. So consider the computational problem that someone gives you an n by n matrix of signs, and you have to compute or estimate the sign ring, what is the minimum possible rank that you can get by assigning values with the right signs. So it's known that to compute it exactly, this is NP hard. It's probably much harder than NP hard. It's not known that this problem even lies in NP, but it's at least NP hard. And it seems that it's hard even to approximate it, although there are no known hardness result. And here the analysis gives us an efficient deterministic algorithm that will approximate this sign rank. Well, not so well. It will be up to a factor of n over log n, but at least it does something non-trivial. So it will tell you some number, and it will give us an approximation of the sign rank, which can range between 1 and n by a factor of n over log n. Okay. So something quick about some proofs, and I'll have to decide what I skip and what I don't, but let's see. So so here is this upper bound for f and d. I tell you that it's at most constant n to the 1 minus 1 over d. So what does this mean? Whenever you give me an n by n matrix of signs with VC dimension d, then the sign rank is at most n to the 1 minus 1 over d. So somehow we want to get a small sign rank. And I'll try to give an outline. So it's not very, I mean, it uses quite some machinery, but it's not complicated, but we don't have, nothing is simple in the last 10 minutes of a lecture. So I only want to give you the impression that if I would have had another 20 minutes, then maybe you would have been able to follow. So let me try to give you this impression. So suppose we have a matrix A, an n by n sign matrix, and the VC dimension is D. Then by a known lemma of that was proved several times. In fact, some version was proved by Vapnik and Chevronenkis, and precise versions by Sauer, and independently by Perles and Chelach. Actually, Perles is the only one who proved it independently twice. There is a nice story here, but let me just leave it with this obscure sentence. So it can be shown that on any set of k columns of A, the number of different projections that you see is at most k to the d. So this is because the VC dimension is d. This is some combinatorial lemma. Then there is a very nice result by Welzel that was slightly extended by Chazelle and Welzel and improved again by logarithmic factor by plugging a result of Hausler in this proof of Welzel. And this says the following somewhat obscure statement, but I'll give an example, that there is a, if we know that indeed the number of projections on any k columns is most k to the d, then there is a spanning tree on the rows of A, so that for every column, the number of edges of the tree that are not uniform on that column is small. It's most n to the 1 minus 1 over d. Here is an example. I know that this does not make much sense. So here is a matrix, and think about this tree as a Hamilton path. So that's the Hamilton path you see. And now it claims that here, for every column you choose, then on almost all, well, on all edges of this tree, on all the 3 edges, but at most 2, then this column is uniform. So for example, if we look at the first column, then on this edge, it is uniform, it's 1, 1. And on this edge, it is 1, 1. It is not uniform only on the first edge. So this is true in general. And then there is some trick that, let's not worry about it, that we may assume that this spanning tree is a path by some Euler, well, by something simple. And if you think what this says, it says that if we have this matrix with small VC dimension, then there is a permutation of the rows of this matrix. So we have some permutation. This is basically the Hamilton path. So this is a permutation of the row. So that if we look along any column, the number of sign changes we see along the column is small, is n to the 1 minus 1 over t, because the number of sign changes is the number of edges of this Hamilton path on which this column is not uniform. Okay? So this means, again, that if we have this matrix, sign matrix, the VC dimension is small, we can permute the rows, and of course by permuting the rows we didn't change the sign rank, so we permute the rows, and now we don't have too many sign changes in every row. And now what we do is that we assign each row of this permuted matrix with a point, pi, in the s plus 1 dimensional space, where s is the number of sign changes in a column. And this point is a point on what's called the moment curve. So just for row I, it's a point 1, I square, and so on, up to I to the s. And then for each column j, we look where we need sign changes, and we assign to it a polynomial that changes signs exactly in these places. And we can have a polynomial of degree at most s, because we need only s sign changes, so we need it to be 0 in the places that we specify, and therefore we can choose this polynomial. As I said, in such short time, you're not supposed to really follow. So if you follow, it means that something is, I'm not doing something right, but you are supposed to really get what's going on. And now you see that here, if we just, this basically gives us the sign rank, because now if we take the n by n matrix B, which is a product of the n by s plus 1 matrix whose rows are the points pi, and the s plus 1 by n matrix whose columns are the coefficients of the polynomials, then the signs will give us what we need. And the rank of this matrix is, of course, at most s plus 1, because it's a product of an n by s plus 1 matrix with an s plus 1 by n matrix. So at least I think this gives some idea of what's going on in this proof. And now let me say something about what's going on in the lower bound proofs for this maximum possible sign rank of an n by n matrix, or maximum possible sign rank of an n by n matrix with a VC dimension d. And that will be the last proof, and then I'll just mention some problems. So here's some notation. So if you have again, luckily those who have been yesterday saw this notation yesterday, but because in general it's not such a good idea to introduce new notation in the last 5 minutes of a lecture, but I think here it's not that bad. So if we have polynomials p1 up to pm, real polynomials in variables x1 up to xn, then the number of sign patterns of these polynomials is we take a point x and we substitute it in the polynomial, and then we have the sign of the first polynomial, the sign of the second, the sign of the third, and so on. And let's say that we allow ourselves to look only at points x in which no polynomial vanishes. Okay? So these are now it's easy to see that this number is at most the number of connected components of the semi-variety of all the points in which no polynomial vanishes, right? Because if we have a connected component, in this connected component, every sign of each polynomial must be constant, because if it changes sign by the intermediate value theorem, somewhere inside the component it will vanish, but it cannot, because this is not okay. And then there is this result in real algebraic geometry by Warren. There were similar results by Milnor and Tom earlier. And he says that if the number of polynomials is at least n, and the degree of each of them is at most k, then the number of sign patterns is at most 4e, so some constant, mk over n raised to the power n, which for m, which is much bigger than n, this could be much better than the trivial bound of 2 to the m, the possible vectors of plus minus 1s of length n. And then using this, one can show, and it's very simple, so it's so short that I'll try to tell it to you in 30 seconds, that there is an n by n matrix, now we don't assume anything on the VC dimension, whose sign rank is at least constant n. So why is this the case? Because the number, so it's a counting argument, the number of n by n sign matrices is 2 to the n square, right? For each place, we can choose either plus or minus, so there are many of them. Now, on the other hand, the number of n by n sign matrices whose sign rank is at most d, so we can write them as a product of an n by d matrix with a d by n. We can think about the entries of these two matrices as variables, and then each entry is just a quadratic polynomial. So this is just the number of sign patterns of n square quadratic polynomials with 2 n d variables. So by Warren, we have an upper bound for this. This upper bound has to be at least a lower bound of 2 to the n square, and the number of variables was 2 n d, and we solve for d, and we get that d is at least some n over 20. And you need some more tricks to get the bounds that I mentioned for bounded VC dimension, but let me skip this. So it just, you can do something, because I still want to mention something about the open problems. And actually, the next slide is the only one where I'm really sorry that it's PDF and not PowerPoint, but let's worry about this when we reach this next and final slide. So here are some open problems. So the first conjectures that I mentioned, here I wrote it in a little bit different way, is it's a maximum possible sign rank of an n by n sign matrix with VC dimension d up to logarithmic factors is n to the 1 minus 1 over d. So we know it for d equals 1, it's easy. For d equals 2, it follows from the things that I mentioned. The upper bound holds for every d. This is what I tried to sketch. And the lower bound actually also holds if we replace the VC dimension by a relaxed related condition. And let me not say what this condition is, but it's also something that is natural. Then there is this question of finding an explicit n by n matrix with a sign rank that is at least linear in n. By counting, we know that there is such a matrix, and but it will be nice to get some explicit example. Now there is this problem of finding a better approximation algorithm for the sign rank of a given matrix, and so this I think is very interesting, or to prove a hardness result that if say p is not np, then it's hard to approximate the sign rank of an n by n matrix up to a factor of n over log n, or up to a factor of n to the 1 minus epsilon. I definitely believe this is a case, but we don't know to prove it. And the final problem I'll mention is a problem that I had about 3 weeks ago, and I found some solution which I think is not optimal, but only you can be the judge of that. And this is how to pronounce the name Łojasiewicz. And with this, I'll finish, and thank you for your attention.
Thank you very much. Now it's time for comments, questions. Proszę bardzo.
I have one question about this schedule of turn one proof with use polynomials. That I get it right. The idea is to see that these sign ranks as we can produce this by taking equation of polynomial type, and we take with sign pattern. It is polynomial at this point is plus or minus. Yes? Mm-hmm. And we see that we know that this such varieties is a finite number, and we know it if we go outside these varieties, this one is 0. Yes?
Right.
So this way we just see that this connection between these planes and these sign rates is correct?
Yeah, so in general that's correct. So the idea is indeed to say that each entry of the matrix is a quadratic polynomial, so the sign is a sign of the quadratic polynomial, and then to get the lower, so then the upper bound follows from these bounds in real algebraic geometry, and for the lower bound you have to produce many, so I showed it only for the basic case, but if you want to do it for fixed VC dimension, you have to show that there are very many sign matrices that have VC dimension 2, for example. And then we can compare the lower bound to the upper bound and get this and get the bounds that we want for the sign ring. But you're right, the connection is that indeed just the entry is a sign of the sign of the entry is a sign of some quadratic polynomial.
Next.
Tell something about the sign random matrix.
So I'm not sure if I heard it. Random, yeah. So for a random matrix, because of this counting argument, it basically says that a random matrix with very high, a random sign matrix with very high probability, it will have sign rank linear, at least n/20 maybe. And on the other hand, a random matrix with high probability, the VC dimension will be roughly log n. So this.
We have some time. We can just talk to Professor Alon for a while. Thank you very much again, and thank you very much for the lecture.
Thank you.